you for attending this tutorial. Before I get started, I hope you and your families are keeping safe and healthy in the face of this global pandemic. In this session, I'm going to report to you TSMC packaging technologies for chiplets and 3D. This is the outline of my presentation. I'm going to start with a brief introduction of TSMC packaging technology, 3D fabric, and the new industry transition. Then I'm going to discuss the new development, including the packaging system scaled up and the interconnect scaled down. Later, I'm going to move to the new heterogeneous integrations, which leverage our 3D fabric technology to provide advanced thermal solutions and also to integrate new components such as silicon photonics. And then I'm going to do a summary. This is a brief introduction of TSMC system integration technologies. We have a new name for the platform, 3D Fabric. It aims to provide cost-effective, good performance, power, form factor, also short time to market with flexibility and scalability. The 3D Fabric has two parts. One is front-end 3D, the other one is back-end 3D. The front-end 3D aim to integrate, partition the chips of SoC to help to sustain Moore's law. And the other part is to provide heterogeneous integration capability to integrate the SoC and dissimilar chips. Afterwards, this SoIC can be further integrated with InFO or CoWoS to provide the whole integration solution. There are several versions of technology structures for each technology groups. For example, CoW, which stands for chip-on-wafer stacking, and wafer-on-wafer WoW stacking structures for SoIC, and also for chip-first, which is InFO integration. InFO-R stands for RDL interconnect, whereas InFO-L, which adds LSI to the RDL interconnect to enhance the bandwidth of the interconnect. And same thing for CoWoS, which is for chip last. Certainly, we don't do this to confuse you. Each version of technology can be more suitable for some applications. We want to do good optimization between main core technology and customized solution to meet our customers' wide application needs. Since we started working on our advanced foundry packaging technologies for many years, we grow and enrich our 3D fabric technology platform to drive new applications such as AI, 3G, HPC, and autonomous driving, etc. We see a new transition for semiconductor industry from CMOS to CSYS. CSYS stands for complementary systems for SoC and chiplet integration. This not only because of many analogies between the two. We can also leverage SOG technologies and infrastructures when working on CCs. In the next session, I will update you the 3D fabric technology development result, which includes system envelope scaled up and the interconnect pitch scaled down. This slide shows the new addition of packaging structures such as InfoB and some examples of packaging envelope increase such as InfoOS and CoWoS S that I'm going to discuss in the following. InfoB, B stands for the bottom part of InfoPub. It's a new Info family member for smartphone applications. It leverages our high-volume InfoPub technology and manufacturing experiences and provides your customer the flexibility to stack DRAM package on it at their contract manufacturer size. InfoB's package can be less than 450 micron in thickness and can house a mobile SoC chip with size up to 135 mm square in a small 14 by 14 info package to meet the most stringent form factor requirement. InfoB will be available in the second half of this year. InfoOS update for HPC chiplet integration. Our InfoOS offers a minimum of 2 by 2 micron pitch and up to 5 layers RDL with a very fine 130 micron pitch copper bump. We started mass production for Info at the size of 1.5 times of reticle since 2018. And in between, we also qualified a 1.7 times reticle version in later part of last year. And in this year, we're going to provide you a new chiplet skin with 2 plus 8 chiplets. And it has a 2.5 reticle size. It's about 51 by 42 millimeter. Substrate size 110 millimeter square. This will be available this year. As you can see in this slide, we can grow InfoOS envelope fairly quick to enable high performance needed by HPC. This again is achieved by leveraging our many years of experience on info development and manufacturing. To further drive to ultra-high bandwidth chiplet integration, we add LSI, which stands for Local Silicon Interconnect, to our InfoOS by leveraging both Info and CoWoS technologies. This new feature drives I/O, pad pitch, RDL pitch, and bump pitch all to new high level. This solution is available already in this year. Since super high-end systems, such as supercomputers for exaflops compute, like one announced a couple of days ago, which is like the tip of a pyramid, can often drive therefore increase the market demand for HPC, infrastructure, and consumers, etc., toward the bottom of the pyramid. Here we propose two new technologies for this application. They are SOIS, which stands for System on Integrated Substrate, and InFO SOW, System on Wafer. They both again leverage our InFO process capability and technology maturity to achieve the goal. InFO SOIS leverages InFO to build advanced RDL layers on top of supporting simple substrate to form a new substrate for high performance, actually super high performance application. And we can stack free chip components, packaged components like InFO or CoWoS, passives, and so on and so forth. Those are the known good dies on the new substrate. And InFO technology enables higher density RDL design rule comparing against conventional substrate. And also because of the maturity of InFO technology, we can quickly achieve very high yield for very large size substrate. For example, 91 millimeter square and 110 millimeter square. We can achieve high yield in short period of time. High quality copper interconnect built with InFO technology also gives us important advantages in lower insertion loss, as you can see from the attached table. SOIS shows 25% to 30% lower insertion loss comparing with conventional substrate over a wide temperature range from 25 to 125 degrees C at 28 gigahertz and also 50 gigahertz respectively. SOIS yet has another advantage over conventional substrate, which is the high density routing capability with finer line pitch, which is in general less than 10 micron pitch, and via size to gain more SerDes pairs and mitigate signal crosstalk. A much smaller mesh hole on power ground planes showed significantly better return loss. It's not to our surprise that SOIS has robust reliability. We use a 91 millimeter square mechanical TV to evaluate the SOIS reliability. As you can see in the table, we passed package level reliability tests and microstructure sanity check after the reliability tests, showing again very good robustness in reliability. The second example is the InFO SOW, which is a full wafer system integration with non-good dies, compact size with integrated power module and thermal modules. We leverage InFO technology from its maturity, high bandwidth density, low latency, chip-to-chip communication, and a low PDN impedance. Here is the first heterogeneous integration for compute, I/O, memory, passive, etc. chiplets. This slide shows the benchmark of info SOW versus conventional free chip MCM multi-chip module. Higher bandwidth density comes from superior line density due to the fine pitch RDL generated by info, and the better power efficiency with very low PDN impedance. Simplified and low-profile structure can be built. Here we eliminate both substrate and PCB. Since this is a super large system utilizing the full wafer size, we need to check for good process uniformity in R and C, which is shown on the left side. Higher quality copper trace against substrate, again coming from info process, enable lower loss, insertion loss, and significant power savings, tested at 28 GHz for various trace lengths. This slide summarizes info system on wafer technology. SOW's superior performance in electrical, power saving, compact system with thermal solution and the power module push the top of the envelope and the tip of the pyramid up high for our industry. In the next few slides, we'd like to update you our CoWoS technology. Its general purpose is to integrate SoC chiplets and memories such as HBMs. With 1 decade of production, with high yield and premium quality, we continue to enrich the interposer features with extended envelope. This is for HPC application, of course. This slide shows the rapid progress of CoWoS technology. You can see from 2011, 5 generation technology migration in 1 decade, along with interposer size is more than tripled. Total transistor count is 20 times more. Memory capacity grows 8 times. We expect this progress continue in the future for ever-increased HPC demands. When package envelope continues to increase and with SoC scaling, the CPI issue, chip package interaction, becomes more challenging for free chip MCM. For CoWoS, however, silicon interposer serves as a stress buffer. CPI stress induced is significantly reduced by 60%, showing CoWoS is much more immune to CPI. This slide shows our leading CoWoS solution for HPC. We qualify a 2500 mm² size silicon interposer, along with electrical performance enhancers, thick metal, and embedded deep trench capacitor, plus 8 HBM2E to further push HPC. Along the years, we see larger number of HBMs of newer versions from multiple suppliers requested by customer to drive HPC system power, speed, and memory bandwidth. This poses challenges. With industry longest R&D and manufacturing experiences, we prove that we can continue to make it happen. One interesting thing, CoWoS has been categorized as a 2.5D solution. Pretty soon, with the integration of SOIC, we see another quantum jump in the challenge and benefits. Just wonder how we name it. Based on customers' input, it's very desirable to shorten design cycle time and faster time to market for CoWoS. So we developed what we call STAR, which means Standard Architecture, to enable this. We have seen 100% success rate for STAR adopters in 2020. We will provide more flexible design options, and we expect adoption rate will grow 4 times this year. In addition, we would like to unify our 2.5D solutions for high-end HPC applications with CoWoS L to best optimize cycle time, year learning, system performance, and the economics of scale, etc. What is CoWoS L? We leverage InFO and CoWoS technology and add local silicon bridge as well as other chiplets, including passives at flow 1, to connect chiplets on flow 2. This structure increases communication bandwidth with LSI and performance over power with passives at the first floor. The solution is expected to be available in 2022 and 23 timeframe. On the 3D chip stacking front, we have been developing chip on wafer on the right-hand side and wafer on wafer technologies shown on the left side to support various applications. The first application for both COW and WOW stacking is HPC. We are in the process of delivering N7 on N7 COW technology by the end of this year and plan to do M5 on M5 COW next year. In addition, we are targeting WOW technology for logic on DTC's integration. For that, we have successfully demonstrated good power droop reduction at the system level testing. This is the current plan to develop SOIC to go with SOC nodes. The first line shows SOC development and the delivery schedule. Then we see for SOIC, COW starts delivery this year for N7 and N6 first. Hopefully, SOIC schedule will gradually align with SOC in COW scheme, and hopefully for WOW as well. For WOW, current schedule is somewhat behind COW. On SOIC design rule, we plan to scale SOIC bond pitch 70% node to node, enabling bond density doubling again per node. That way we can achieve 2x bandwidth density scaling per node and the EEP energy efficient performance per node migration for more than 1 decade in the future. SOIC cadency is also planned for 2 years per SOIC node. In short term, however, our SOIC bump pitch scaling may somewhat accelerate. This is because of two reasons. First, the node-to-node design rule was meant to match with SOC node. That means 9-micron pitch for N7, N6, and the 6-micron pitch for N5, N4, etc. However, their schedule is not aligned yet. Leading customer request to align SOIC schedule with SOC node. An SOC node is ahead as shown in previous slide. And the second reason was that our process is fairly scalable. We have shown the feasibility of sub-micron pitch bonding. So the schedule for the first few SOIC nodes may be squeezed a bit. This slide shows our preliminary study of our sub-micron SOIC bond pitch stacking result. The bonding interface is shown here. Good bonding interface with promising reliability is obtained. This sub-micron pitch SOIC bonding has big implication in the future. It can enable direct integration of SOIC bond and SOC BEOL in the connect. It has a long-term deep chip partition implication. Although SOIC is considered a front-end process, we expect a trend to grow its envelope, just like the back-end packaging cases. Bigger SOIC can be integrated with either more or larger units in 2D direction or more layers in 3D in the third dimension to integrate more memory capacity and all high functions. However, thermal wall has to be addressed to remove the heat accumulated in the 3D stacking. Next, we will discuss some of the new applications provided by leveraging 3D Fabric platform to enable innovative solutions to address new challenges such as thermal wall solution and the silicon photonics integration. This slide shows conventional thermal solution migration paths. It can enable good thermal resistance reduction as shown here. This is done by pushing for lower and better TIM, which stands for thermal interface material. From gel type tin to film type and eventually to liquid metal tin. However, 3D stacking is significantly more demanding in thermal solution than ever before. We need to continue to explore new and better solutions. This slide discusses the new thermal solutions we proposed that leverages our 3D Fabric technology to further drive thermal resistance lower. We first show illustration of conventional approach at upper left corner with liquid metal tin located between silicon TDV, that stands for silicon thermal test vehicle. In fact, that means that is SOC, and copper lead. We then evaluate 3 new schemes. First, we replace copper lead with silicon lead that has preformed microstructures such as trench or pillar to allow liquid coolant to approach closer to the heat source at the bottom to remove heat more effectively as well. We also study the new oxide bonding to replace the liquid metal tin to further reduce thermal resistance. And we even evaluate the case that we eliminate the bonded silicon lead and put silicon microcooler located at the back of the SOC, allowing liquid coolant approach even closer to the heat source to hopefully better remove the heat efficiently and effectively. Here again, we want to temporarily name this solution silicon lead liquid metal bond to SOC. This is scheme A. Oxide tin is scheme B, and when both oxide tin and the silicon lead is removed for this direct water cooling case, this is scheme C. This slide summarizes the evaluation result. I apologize for the busy chart. Okay, the first 2 columns represents the liquid metal tin case, and the next 2 columns shows oxide tin case. The last 2 columns represent direct water cooling case. For each scheme, we have 2 liquid flowing rate. We can just focus on one of them. Take 2 liters per minute flow rate as an example. We compare the liquid metal tin versus oxide tin versus direct water cooling case. The tin itself shows 4. This is okay. I didn't include the unit. So this is the total resistance 4 for the liquid metal tin, 1.5 for the oxide tin, and it's 0 because for direct water cooling, because the tin is totally eliminated. So we end up with the total thermal resistance showing from 31 all the way down to 22 for the case of direct water cooling, showing big improvements. Here is a summary of our integrated silicon microcoolant study. 3D chip stacking requires more aggressive thermal solution. Oxide tin, by leveraging our SOIC fusion bond, can greatly reduce the best known liquid metal tin. Its resistance reduced by more than 50%. Further improvement can be achieved by direct water cooling, and a kilowatt power level heat dissipation solution can be achieved by the two proposals, Oxide Team and the DWC. System mechanical integrity need further study. Now let's move to my last topic, the integration of silicon photonics. The explosive growth of internet traffic has driven data centers to turn to SiPho for its high speed and low power consumption. And we propose a new CUP, stands for Compact Universal Photonic Engine, by leveraging our 3D fabric technology. We propose CUP to address the need for a wide range of silicon photonics integration applications to address performance, power, and volume cost challenges. This slide is a quick illustration of the evolution of silicon photonics package migration from pluggable to onboard optics to CPO co-packaged optics. Drive to the closer proximity between those key components for bandwidth, power efficiency, and even cost, which can be associated with the super large size substrate for CPO case. And this is the opportunity that we leverage our 3D fabric technology to provide values. Monolithic integration can achieve good data rate and power efficiency. However, the technology node disparity between EIC and PIC, electronic die and the photonic die, is the main economic challenge for it. CUP is our solution proposed for the heterogeneous integration of EIC and PIC to enable close proximity to minimize electrical coupling and optic coupling loss. This slide compares two 3D stacking schemes, CUP versus microbump stacked. CUP has significantly lower parasitic at the EIC-PIC electrical interface. 80% lower capacitance can be achieved. In the meantime, 51% reduction in PDN impedance comparing with microbump with TSV, and a 92% reduction, again, with microbump associated with wire bonding. This slide compares two 3D stacking schemes. One is CUP, the other one is conventional 3D stacking with microbump. CUP shows significantly lower parasitic at the EIC-PIC electrical interface. 85% lower capacitance can be achieved against microbump. And for PDN impedance, CUP enable 51% reduction comparing with microbump integrate with TSV, and a 92% reduction from microbump integrate with wire bonding. This slide compares power consumption of CUP versus microbump, either with TSV or with wire bonding. COOP achieves 40% lower power consumption at the same speed, and also reach 170% speed gain at the same power. This slide evaluates the optical interface of a photonic engine. Light can be coupled with either vertically with grating coupler or horizontally with edge coupler. GC as a surface coupler requires cleanness and integrity of the optical path from grating surface all the way to the fiber core. For EC, on the other hand, care must be taken to prevent the expanded optical mode from overlapping the bulk silicon underneath SSC. At TSMC, we leverage our 3D fabric technology to innovate COOP photonic engine so that GC and EC can be built with essentially the same structure. And GC is designed in COOP with optical paths intrinsically sealed with dielectrics all the way to the fiber attachment unit, achieving very low insertion loss of 1.03 dB for TE. And for EC application, we avoid optical loss due to being overlapped with underneath silicon, achieving insertion loss of approximately 0.6 dB for both TE and the TM modes at 1310 nanometer wavelengths. Here is the summary. TSMC 3D fabric technology platform continues to drive packaging envelope scale up and 3D interconnect density scale down to drive energy efficient performance. Thermal wall could also be addressed for more demanding 3D stacking by new microcooling system ISMC and DWC. Leverage 3D fabric to integrate innovative COOP for silicon photonics component integration to further enhance system performance and function for HPC. I would like to express my sincere appreciations to TSMC colleagues in the following organizations for their strong support. Collaboration with supply chain partners are also acknowledged. And thank you for your